AI agents are becoming increasingly autonomous. They call APIs, modify data, interact with infrastructure, and make multi step decisions. But testing them is still surprisingly primitive. Most teams test an agent with a handful of manually written prompts. That tells you whether it works on the happy path. It doesn't tell you what happens when the agent encounters an ambiguous instruction, a destructive tool, a tool failure, or a scenario it wasn't explicitly designed for. That's the problem I'm trying to solve with Agent Reliability Engine. Agent Reliability Engine is essentially a CI/CD pipeline reliability layer for autonomous AI agents. Instead of simply asking whether an agent produces a correct answer, the system generates adversarial scenarios, executes the agent in a controlled environment, captures what actually happened, analyzes the behavior, and turns that into reliability metrics and regression signals. Let's look at the architecture of this entire platform. This architecture is intentionally event driven to increase scalability and reliability. The scenario generator takes the agent's system prompt, tool definitions, and task domain and generates adversarial scenarios. These scenarios are persisted in the scenario store and published to Kafka through the scenario jobs topic. This means scenario generation and execution do not have to be tightly coupled. Agent runner can scale independently based on evaluation workload. The agent runner consumes these jobs and starts a temporal workflow. Temporal is responsible for durable orchestration, retries, timeouts, and maintaining the execution state of a multi-step agent event. The workflow driven drives the workflow drives execution inside a controlled sandbox. In a production implementation, this could be backed by stronger isolation technologies such as using containers, gvisor, or virtual machine style execution. For the prototype, we are using a controlled execution environment. Every important action produces a trace, LLM calls, tool calls, state transitions, latency, and failures. The important architectural boundary here is that the trace capturer writes the trace store. The analyzer does not need to be coupled directly to the execution process. It can query the persisted trace independently. Let's look at the system and the prototype. This is where the system moves from observability to reliability analysis. The analyzer looks at the execution evidence and classifies failure modes. For example, here we can see that the agent attempted a destructive operation without the required confirmation. Instead, instead of running a raw log, the analyzer produces a structured reliability event. That reliability event is published as secondary Kafka topic called analysis events. And this is intentionally fan out rather than a sequential pipeline. The scorecard service and the regression tracker consume the same event independently. The scorecard gives us the current reliability state of an agent, and and the regression tracker gives us historical comparison across variants. The important distinction is that this isn't another chatbot. The LLM is only one single component. The actual product is the reliability infrastructure around the agent. We are trying to answer questions like what did the agent actually do? Why did it fail? Is the failure critical? Did the latest version become less reliable? And should this agent be allowed to move further through a deployment pipeline? As a future scope, we would eventually like to take this and make it into a reusable package, a CI/CD component that acts as a reliability gate for all of the autonomous agents, such as Cloud Code and all that stuff. So the core idea is simple. Autonomous agents need something analogous to CI/CD, not just to test whether they can complete a task, but to continuously test whether they can fail safely. Agent reliability engine is our prototype towards that reliability layer. Thank you so much.